My dear children, welcome back to my channel Information Nest, and I welcome you to the amazing world of solute solvents and solutions. Imagine this: you mix sugar into water and it disappears. You sip a soft drink and it tastes sweet, fizzy, and refreshing. You clean your hands with sanitizer and it dries up in seconds. What is the magic behind these everyday wonders? It's science, the science of solutions. In this chapter, we will dive into a world where tiny particles come together to form mixtures that power our lives, from the water we drink to the medicines we take. You will discover what makes a solute dissolve, why is water called the universal solvent, how do solutions help in cooking, cleaning, and even curing diseases. Get ready to explore the invisible chemistry that makes the visible world work. This isn't just about definitions, it's about unlocking the secrets of how things mix, react, and transform. Let's begin our journey into the amazing world of solutes, solvents, and solutions where science meets everyday life. Hey, curious minds, you ever tried adding sugar to your tea and then a little more and a little more until it just sits there at the bottom, refusing to dissolve? That's not your sugar being stubborn, it's science in action. When a liquid like tea cannot dissolve any more solute like sugar, it becomes a saturated solution. Yup, it's full, like a stomach after a Diwali feast. So, what do you do if you want it sweeter? You have got two options: heat the tea or add more water. Why heat? Because warmer liquids dissolve solids faster. Just think of hot chocolate. Ever tried making it with cold milk? It's like convincing your little brother to share his chips. Not happening. Did you know? The ocean is one giant solution, salt dissolved in water. And if you ever swim in the Dead Sea, you will float like a rubber duck because it is super saturated with salt. A quick recap here, children. A saturated solution is when no more solute can dissolve. Heating helps dissolve more. Water is called the universal solvent. It is like the superhero of liquids. Why did the solute break up with the solvent? Because it said, you're just not dissolving my problems anymore. So, next time your tea stops sweetening, do not panic. Just remember you have reached saturation. And that's not just a kitchen moment, it's a chemistry moment. Stay curious, stay sweet, and let's keep exploring the amazing world of solutions. Ever wondered why sugar disappears in water but just sits there in oil like it's sulking? Well, it's not being moved, it's molecular science at work. Let's talk about polarity. Polarity is all about how electric charge is spread across a molecule. If the electrons are unevenly shared, like siblings fighting over a remote, the molecule becomes polar. Water is a classic example of a polar solvent. And guess what? Sugar and salt are polar too. So when they meet water, it's like best friends reuniting. They mix beautifully. But oil is non-polar. It's like the chill cousin who doesn't care about electric charges. So when sugar or salt tries to dissolve in oil is like, sorry buddy, you're not my type. Like dissolves like. Polar loves polar. Non-polar loves non-polar. But mix the two, no. It's like trying to blend water and oil, literally. Why didn't the salt go to the oil party? Because it couldn't find a solution. So next time you stir sugar into your tea or wonder why salad dressing separates, remember it's all about polarity, tiny molecules, big personalities. Let's talk about a liquid so powerful, so versatile. It's called the universal solvent. Nope. It's not some fancy chemical from a superhero lab, it's water. Why is water such a good solvent? because it can dissolve more substances, solids, liquids, and even gases than any other liquid on Earth. Salt, sugar, oxygen, even acids, water has got it covered. The science behind it is that water is a polar molecule. That means its electric charge isn't spread evenly. It's got a slightly positive side and a slightly negative side, kind of like a magnet with personality. This polarity helps water surround and pull apart other polar or ionic substances. It's like water giving solutes a big molecular hug and saying, "Come join the party." Water helps plants transport nutrients. It helps us digest food. It is involved in chemical reactions, environmental cycles, and even the weather. Did you know your body is about 60% of water? So technically, you're walking around with the universal solvent inside you. No wonder you're so good at solving problems. Why did water apply for a job as a chemist? Because it heard it was the solution to everything. So next time you stir salt into your soup or watch rain soak into the soil, remember water isn't just wet, it's wonderfully wise. It's the silent scientist working behind the scenes in every drop. Stay curious, stay hydrated, and let's keep exploring the amazing world of science around us. You wondered why a water bottle looks like a tall cylinder and not a round one? Let's dive into the science of design and function, where shape meets purpose. Cylindrical bottles are everywhere and for good reason. First point is it is easy to grip. Your hand wraps around it like it was made for you. Second positive reason is it is efficient to store. They fit neatly in bags, cup holders, and fridge racks. And the last and final point is that it has uniform pressure distribution. So they do not bulge or burst when filled. Now imagine a spherical bottle. It would roll off your desk, wobble in your backpack, and be nearly impossible to hold without dropping it. Not exactly hydration friendly. Cylinders are also used in rockets, pipes, and even toothpaste tubes because they are strong, stable, and space smart. Why did the spherical bottle get rejected from the factory? Because it just couldn't stay in shape. So next time you take a sip from your bottle, remember its shape isn't just stylish, it's scientifically smart. Design and function go hand in hand, making everyday objects work better for you. Ever sipped ORS when you're feeling low on energy? Notice how every sip tastes exactly the same. No surprise salt bombs or sweet patches. That's not luck, that is science. Let's talk about mixtures. When sugar and salt dissolve in water, they spread out evenly. This creates a uniform mixture, also called a homogeneous solution. It means every drop has the same composition like a perfectly blended smoothie. Now imagine if ORS were a non-uniform mixture. One sip might taste like ocean water, the next like candy syrup. Yeeks! That's a roller coaster your taste buds didn't sign up for. Real life examples of uniform mixtures are ORS, oral rehydration solution, lemonade, salt water, even the air we breathe. They all have one thing in common, that is consistency. Did you know the word solution comes from Latin solutio, meaning to loosen or untie. So when solutes dissolve, they are literally letting go and spreading out. Why did the salt and sugar become best friends in water? Because they knew how to mix things up evenly. So next time you stir your drink or mix ingredients, remember uniform mixtures are the secret to smooth taste, smooth science, and smooth solutions. Let's do a quick experiment in your mind. Imagine you take a spoonful of chalk powder and mix it into a glass of water. Stir, 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 and then wait. What do you see? Here is what happens. The chalk does not dissolve. It floats around around for a bit, makes the water look cloudy, and then settles at the bottom like it is tired of drying. This is called a uniform mixture, or in science terms, a heterogeneous mixture. It is like chalk saying, water, we are just too different. I need my space. Real life examples of non uniform mixtures are sand in water, sawdust in water, oil in water. They break up faster than a bad friendship. In all these cases, the components do not spread out evenly. You can see the difference. You can feel the layers. Did you know milk might look uniform, but under a microscope, it is actually a colloid, a special kind of non uniform mixture where tiny particles stay suspended. Why didn't the chalk powder get invited to the solution party? Because it just couldn't blend in. So next time you mix something and it does not dissolve, don't be disappointed. Be curious. You have just discovered the fascinating world of heterogeneous mixtures, where not everything is meant to mix. Stay observant, stay scientific, and let's keep exploring the amazing world of. Right, young scientist in training. Let's talk about something we all do, mixing stuff. From making lemonade to stirring paint, mixtures are everywhere, but not all mixtures are created equal. Let's compare two types, uniform and non-uniform mixtures. So, what is a uniform mixture? Well, imagine you stir sugar into water. It dissolves completely, right? Every sip tastes the same, no surprise sweetness or salty patches. That is a uniform mixture, also called a homogeneous mixture. It looks clear, consistent, and the particles are spread out evenly. Examples: salt water, ORS, sugar water, basically anything that looks the same throughout. Now, let's flip the script. What if you mix chalk powder in water? You stir and still see cloudy water with powder settling at the bottom. That is a non-uniform mixture or a heterogeneous mixture. It is uneven, messy, and the particles do not spread out nicely. Examples: chalk water, sand in water, oil in water. You can actually see the different parts. If it looks smooth and even, it is uniform. If it looks patchy or layered, it is non-uniform. Why did the chalk and water break up? Because they just could not mix things up evenly. So next time you stir something, take a closer look. You're not just mixing, you're doing chemistry, uniform on uniform. Every mixture tells a story. Let's keep exploring the science around us, one mixture at a time. All right, team, you just tackled a quick quiz on mixtures, and I must say you're mixing knowledge like pros. Let's walk through those questions together and make sure the science sticks. Is lemonade a uniform or non-uniform mixture? Your answer should be uniform mixture. Why? Because sugar and lemon juice dissolve evenly in water. Every sip tastes the same, no surprise. Sour blast or sugar clumps, that's what we call a homogeneous mixture. What happens if you leave chalk water disturbed for an hour? The chalk settles at the bottom. Chalk does not dissolve in water, it is insoluble. So, when you leave it alone, gravity does its thing and the chalk sinks. That is a classic non uniform mixture, or heterogeneous if you want to sound fancy. And why doesn't oil mix with water? Because oil is non-polar and water is polar. It's like trying to mix introverts with extroverts at a party. They just don't vibe. In science, we say like dissolves like. Polar substances mix with polar solvents and non-polar with non-polar. Oil and water, total opposites. Why did the oil break up with water? Because it said we are just not on the same wavelength. So next time you stir, shake, or sip something, think about what is happening behind the scenes. Is it mixing evenly, settling out, refusing to blend? That is science in action, and you are already decoding it. Let's keep exploring, experimenting, and asking questions, because in science, every answer leads to a new mystery. Science explorers, let's stir up some knowledge today, literally. You ever mixed sugar into water and watched it disappear? That's not magic. It's a solution in action. So, what is a solution? A solution is a uniform mixture where one substance dissolves in another. In simple words, everything blends evenly and you cannot tell one part from another. Let's break it down. The substance that dissolves is called the solute. Think sugar or salt. The substance that does the dissolving is the solvent. Most often it is water, a universal mixture. And the final smooth blended result, that is your solution, like sugar water or ORS. Here is a memory tip to keep it crystal clear. Solute is small, solvent surrounds, together they solve the mix. Some real life examples are salt in water, lemon juice in water, even oxygen in blood. Solutions are everywhere, from your kitchen to your bloodstream. Why did the solute go to therapy? Because it felt like it was losing itself in the solvent. So next time you make something and it disappears into the liquid, smile. You have just made a solution. It's a science you can sip, stir, and study. Let's keep mixing it up and exploring the amazing world of chemistry around us. Say you are mixing two liquids like vinegar and water. You ever wondered which one becomes the solvent and which one is the solute? Here is the rule. The liquid in larger amount is the solvent. The one in smaller amount is the solute. So in vinegar and water, if water is more, it is the solvent. Simple, right? It is like the host of the party. Whoever has got the bigger space gets to set the vibe. But wait, can gases form solutions too? Absolutely. In fact, you are breathing one right now. Air is a gaseous solution. Solvent, that is nitrogen, it is the most abundant gas in the air. Solutes like oxygen, carbon dioxide, argon, and a few others. They're all mixed evenly, making air a uniform mixture, a solution you inhale every second. If oxygen were the solvent instead of nitrogen, we would all be way too energized and possibly flammable. So thank nitrogen for keeping things chill. Why did oxygen and nitrogen start a band? Because they knew how to mix well and always stayed in harmony. So whether it is liquids in your kitchen or gases in the sky, solutions are all around you, quietly keeping life balanced and breathable. Stay curious, stay mixed up, and let's keep exploring the amazing science behind the scenes. Let's take a break from the lab and head to the kitchen because today's science is served with dessert. Ever dipped a warm, soft gulab jamun into chutney that's sugary syrup? It's not just delicious, it's a perfect example of a solution. Here's a twist. Even though sugar is added in large quantity to make chutney, it is still a solute. Why? Because sugar is the substance that dissolves, and water, even if it is less in quantity, is the solvent because it is the liquid doing the dissolving. So, yes, sugar may be the star of the show, but water is the one making it shine. Together, they create a uniform mixture, sweet, smooth, and scientifically satisfying. Why did the sugar get jealous of the water? Because water always dissolves the problem first. Solute is small, solvent surrounds, together they solve the mix. Just like gulab jamun soaking up syrup, science soaks into everyday life. So next time you enjoy a sweet treat, remember there is chemistry in every bite. Solutes, solvents, and solutions aren't just in textbooks, they are in your thali too. Stay curious, stay sweet, and let's keep exploring the science behind the scenes. Hey, scientists, ready to roll up your sleeves and stir up some science? Today we are diving into solubility. That is a fancy word for how much of a substance can dissolve in a liquid. Let's find out. How much salt can water hold before it says no more? Here is what you will need. One clean glass tumbler, water half filled, salt, a spoon, and of course your curious brain. Let's get mixing. Add 1 spoon of salt to the water. Stir it well until it dissolves completely. Now keep adding 1 spoon at a time, stirring after each. Watch closely when the salt stops dissolving and starts settling at the bottom. You have reached the saturation point. Time to record your results. Make a table showing how many spoons dissolved before the water gave up. This tells you the solubility of salt in water at room temperature. Warm water can hold more salt than cold water. So, if you heat it up, you might squeeze in a few extra spoons. Why did the salt get rejected by the water? Because it was just too much to handle. So go ahead, stir, observe, and discover. This simple activity reveals a powerful concept. Every liquid has a limit, and you just found it. Stay curious, stay salty in a scientific way, and let's keep exploring the amazing world of solutions. Let's stir up some science. In this activity, we explore how much salt water can hold before it says that's enough. We started with a clean glass half filled with water and added salt 1 teaspoon at a time. Here is what we observed. 1 teaspoon dissolves easily. 2 teaspoons still dissolves. 3 teaspoons, no problem, dissolves. 4 teaspoons, some salt starts settling at the bottom. 5 teaspoons doesn't dissolve at all. It just sits there like it's done trying. This tells us we have reached the saturation point, the maximum amount of salt that water can dissolve at room temperature. Beyond this point, any extra salt remains undissolved, forming a non-uniform mixture. If you heat the water, it can dissolve more salt. Warm water, more solubility. That is why hot soups can hold more flavor. Why did the fifth spoonful of salt get rejected? Because the water said, sorry, I'm full. So next time you're mixing something, remember every liquid has its limit. And you just discovered it through observation, patience, and a pinch of salt. Stay curious, keep experimenting, and let's reflect on what we just observed in our solubility activity. We added salt to water 1 spoon at a time and watched what happened. So, how many spoons dissolved completely? 3. That is the magic number in our experiment. This tells us the solubility limit of water for salt at room temperature. What happened when we added more salt after that? The water said, nope, I am full. Extra salt stopped dissolving and settled at the bottom. That is when the solution became saturated. But why does this happen? Because every solvent like water has a maximum capacity to hold solute. Once that limit is reached, it simply cannot dissolve more. It's like trying to fit more clothes into an already packed suitcase. Concept recap. A saturated solution is one where no more solute can dissolve in the solvent. Any extra solute, it just settles at the bottom, waiting for space that never comes. A funny tip for you all children. If you heat the water, it can dissolve more salt. Warm liquids is equals to more room for solute. Why did the salt stop trying to dissolve? Because it realized it had reached its limit. So next time you stir something and it stops blending, do not be puzzled, be proud. You have just witnessed a key concept in chemistry, that is saturation. Stay curious, keep experimenting, and let's keep exploring the science behind the scenes. Here are some science. Ever kept adding salt to water and wondered how much is too much? Here is what happens. At first, the salt dissolves completely. That is called an unsaturated solution. The water still has room to hold more salt. Keep adding, and suddenly the salt stops dissolving and settles at the bottom. Boom! You have hit a saturated solution. The water is full. Temperature matters. Higher temperature, water can dissolve more salt. At lower temperature, solubility drops. So yes, warm water is more welcoming to solutes like a cozy blanket for molecules. Let's talk about concentration. How salty is your solution? Uh, dilute is nothing but less solute in more solvent. For example, 1 spoon of salt in 100 ml of water. Then if it is concentrated, it means more solute in less solvent. Example, 4 spoons of salt in 50 ml of water. What is solubility? The maximum amount of solute that can dissolve in a solvent. Example, about 5 spoons in 100 ml of water approximately. Dilute is nothing but light and loose. Concentrated is thick and strong. Saturated is full and done. This will be a memory tip. And why did the salt stop trying to dissolve? Because it realized it had reached its limit. So next time you mix something, watch closely. Is it dilute, concentrated, or saturated? You're not just making a solution, you're solving a mystery. Talk about something salty literally. You ever kept adding salt to water and wondered how much more can it take? Yes, here it what happens. At first, the salt dissolves completely. That is called an unsaturated solution. The water still has room to hold more salt. But keep going and suddenly the salt stops dissolving. It settles at the bottom like it is done trying. That is a saturated solution. The solvent has reached its limit. Temperature plays a big role too. Warm water can dissolve more salt, cold water not so much. So yes, heat helps solutes sneak in a little more. Let's talk about concentration. It is all about how much solute is packed into the solvent. If it is a dilute solution, less solute in more solvent. Like 1 spoon of salt in 100 ml of water, think of it as a dainty dose. Concentrated solution. More solute in less solvent, like 4 spoons of salt in 50 ml of water, that is crowded up. Solubility. The maximum amount of solute that can dissolve in a solvent. Around 5 spoons in 100 ml of water approximately. Beyond that, it is saturation time. Now, let me help you uh, by giving some memory mnemonics. Saturated is settled solute, dilute is dainty dose, concentrated crowded cup. So why did the salt stop trying to dissolve? Because it realized it had reached its limit. So next time if you are mixing something, ask yourself, is it a dilute solution, concentrated solution, or saturated solution? Is the solvent still welcoming or has it shut the door? You're not just stirring, you're studying chemistry in action. Science explorers, ready to turn up the heat and stir up some chemistry? Today, we are investigating a sizzling question. Does heat help solubility? Let's find out by experimenting with baking soda and water. Objective to observe how temperature affects the solubility of baking soda in water. Materials that you will need 50 ml of water, a pinch of baking soda, a glass beaker, a laboratory thermometer, a stirring rod, a heating device, and yes, safety first. Let's begin the experiment. Pour 50 ml of water into the beaker. Step 2, add a small spoon of baking soda and stir well. Step 3, observe does it dissolve completely. Step 4, now gently heat the water while monitoring the temperature. Step 5, add another spoon of baking soda and stir again. Step 6, keep observing does more baking soda dissolve as the temperature rises? What is happening? As the water gets warmer, the molecules move faster. This helps them break apart the baking soda more easily, increasing solubility. Most solids dissolve better in warm water. That is why hot tea sweetens faster than iced tea. Why did the baking soda love hot water? Because it knew things would dissolve into something special. So, next time you are mixing something, remember temperature matters. Warm water isn't just cozy, it's a powerful solvent boost. Let's turn up the heat literally and explore how temperature affects solubility. Today's experiment is all about baking soda and water. Simple ingredients, powerful science. Step by step, already we have seen it, but once again I am repeating it. First, we measure 50 ml of water at 20 degrees centigrade. We add baking soda, 1 spoon at a time and stir until it stops dissolving. That is our saturation point at room temperature. Now we heat the water to 50 degrees Celsius. Guess what? The undissolved baking soda starts dissolving again. The solvent's capacity has increased. Then we go further, heat it to 70 degrees Celsius. Even more baking soda dissolves. It's like the water is saying, I have got room for more. So the temperature of the temperature solubility of baking soda will be at 20 degrees Celsius it is least, 50 degrees centigrade more, 70 degrees centigrade most. So what did we learn? As temperature increases, solubility increases. A solution that was saturated at a lower temperature can become unsaturated at a higher temperature. That means heating a saturated solution can help dissolve more solute. It is like giving the solvent a bigger backpack, it can carry more. This principle is used in cooking, medicine, and even in making fizzy drinks. Why did the baking soda love hot water? Because it knew things would dissolve into something special. So, next time you stir something and it won't dissolve, try warming it up. You're not just heating, you're unlocking the science of solubility. Science stars. Before we wrap up, let's quickly revisit the key concepts we have stirred, mixed, and heated up today. Solubility is the maximum amount of solute that can dissolve in a solvent. Think of it as the solvent's carrying capacity, how much it can hold before saying, I'm full. Saturated solution is when no more solute can dissolve. Any extra just settles at the bottom like it's waiting for a table at a packed restaurant. Unsaturated solution is the solvent still has room. You can add more solute and it will happily dissolve like guest arriving early to a party. Temperature effect. It affects most probably the solids that dissolve better in warm solvents. Why? Because heat makes molecules move faster, helping them break apart and mix more easily. Memory mnemonic for this particular concept is hot water hugs more solute. It's warm, welcoming, and always ready to dissolve a little more. Why did the cold water refuse to dissolve the sugar? Because it wasn't feeling sweet enough. So, whether you're mixing salt, sugar, or science, remember temperature, concentration, and saturation are the keys to understanding solutions. Before, modern chemistry labs, ancient Indian sciences like Ayurveda, Siddha, and Unani were already using the power of solvents to heal. Their secret: water, milk, ghee, oils, and even hydroalcoholic extracts, each chosen carefully to dissolve herbal compounds and deliver their benefits deep into the body. Traditional wisdom meets modern science. These natural solvents weren't just chosen for taste or texture, they were selected based on how well they could extract medicinal properties. It is the same principle we use today in chemistry. Solubility matters. Let's bring it to your kitchen. Why does hot tea dissolve sugar faster than cold tea? Because heat gives water molecules more energy, they move faster, collide harder, and break down sugar more easily. It's like a dance floor when the music's faster, everyone moves more. Some real life examples of temperature affecting solubility are making syrup for sweets like jalebi or gulab jamun, dissolving spices in hot oil during tadka, preparing decoctions in Ayurveda, mixing medicines like ORS or herbal teas. In all these cases, heat helps solutes dissolve better, making the mixture more effective. Now, here is a twist. What happens if you cool a saturated solution? The solvent's capacity drops. Some of the dissolved solute may come out of the solution and settle or crystallize. It's like the solvent saying, I was okay with this much, but when I was warm, but now I need to let some go. Hot water hugs more solute. It's warm, welcoming, and always ready to dissolve a little more. Why did the cold tea break up with the sugar? Because it just couldn't handle the sweetness anymore. So whether it is ancient medicine or your morning chai, the science of solubility is always at work. quietly blending tradition with chemistry. My dear children, let's meet someone who turned curiosity into chemistry and tradition into treatment. Dr. Asima Chatterjee. Her inspiration began in Kolkata in the 1920s, surrounded by the vibrant world of medicinal plants and traditional Indian remedies. Her father, Indra Narayan Mukherjee, was a doctor who loved botany. He did not just treat patients, he taught his daughter to ask questions like how do plants heal? What secrets lie in their leaves and roots? And her scientific path was fueled by her early fascination. Asima pursued organic chemistry and phytomedicine, the science of plant based medicine. She believed that India's ancient remedies weren't just folklore, they were scientific treasures waiting to be explored. Her research led to breakthrough in treating diseases like epilepsy and malaria using compounds from the plants like vinca and alstonia. Asima Prem Chatterjee didn't just study science, she blended tradition with innovation, proving that ancient wisdom and modern methods can work hand in hand. She was the first woman to earn a doctorate of science from an Indian university, a true trailblazer. Why did Asima Chatterjee love plants so much? Because they always rooted for her. So, if you have ever wondered how your grandmother's herbal tea works or why neem is used in medicine, remember science starts with curiosity. Just like Asima Chatterjee, you too can explore, experiment, and discover the healing power of nature. Stay curious, stay inspired, and let's keep learning from the legends of science. Let's take a moment to celebrate the brilliance of Dr. Asima Chatterjee, a scientist who turned India's traditional plant wisdom into modern medicine, long before high-tech labs and fancy machines. Her breakthroughs were groundbreaking. She developed Ayush 56, an anti-epileptic drug from a humble aquatic plant called Marsilia minuta. A plant you might walk past without noticing, she turned it into a life changing remedy. She created powerful anti malarial formulations using Indian medicinal plants like Alstonia scholaris, Swertia cerata, Picrorhiza purova, then Cisalfinia crista. These weren't just herbs, they were her chemical allies in the fight against disease. Her secret weapon was the art of using solvents and solutions to extract active compounds from plants. At a time when tools like NMR spectroscopy didn't even exist, she relied on deep knowledge, precision, and patience. Asima Chatterjee didn't just study plants, she listened to them. She believed that India's ancient remedies could be scientifically validated, and she proved it with every discovery. Her work laid the foundation for natural product chemistry, inspiring generations of scientists to look to nature for answers. She was one of the first women in India to lead a chemistry department and received global recognition for her research. Why did Asima Chatterjee never worry about lab equipment? Because she had solutions for everything. So, to all the future scientists out there, remember big discoveries can come from small leaves, white roots, and curious minds. Let's take a deep breath, literally, and dive into the science of gases dissolving in water. You ever wondered how fish breathe underwater? They do not have scuba gear, but they do have science on their side. Do gases dissolve in water? Yes. Many gases like oxygen, carbon dioxide, and nitrogen dissolve in water. Even though oxygen dissolves in small amounts, it's just enough to support aquatic life like fish, frogs, and underwater plants. Uniform or non-uniform mixtures. When gases dissolve in water, they spread out evenly. You can't see the gas particles floating around. They are completely blended. That's make it's a uniform mixture, also called a solution. So yes, The water in a pond or aquarium is not just liquid, it's a gas infused solution that keeps life going beneath the surface. The oxygen fish breathe isn't from the water molecule, it's from dissolved oxygen gas. Nature's chemistry at work. Why don't fish ever run out of breath? Because they always have a solution nearby. So, next time you see a fish swimming gracefully, remember there is invisible science in every drop of water. Gases, solutions, and solubility are quietly keeping the underwater world alive. Let's talk about something that is easy to miss but super important: gas solubility, especially how temperature affects it. And here is a twist: unlike solids, gases behave a little differently when things heat up. Here is the science behind this. Higher temperature is equal to less gas dissolution. Lower temperature is more gas dissolved. So yes, cold water holds more oxygen, and that is a big deal for fish, frogs, and all those underwater creatures. Why does this matter? In warm water, oxygen escapes more easily. That can stress aquatic life, especially in summer or polluted water bodies. And here is a very easy memory tip. Imagine gas molecules as shy guests at a party. In cold water, they feel comfortable and stay longer. In hot water, they get overwhelmed and leave early. This is why aquariums use chillers and aerators to keep oxygen levels high and fish happy. Why don't oxygen molecules like taps? Because they always feel the pressure to leave. So next time you see a pond, a fish tank, or even a glass of soda, remember temperature changes everything, even for invisible gases. Let's take a closer look at two everyday materials, sawdust and sand, and see what happens when we mix them with water. You might think they could behave the same, right? Well, not quite. Here is what we observe. When you mix sawdust with water, it floats. When you mix sand with water, it sinks. So, what is going on here? It all comes down to one key concept: density. Sawdust is less dense than water, so it stays on top like a feather on a pond. Sand is more dense than water, so it sinks to the bottom like a pebble in a glass. This is a great example of non-uniform mixture where the components do not spread out evenly. You can see the difference: floating sawdust, settled sand. Density decides who floats and who sinks. It's like a science version of survival of the lightest. Why did the sawdust refuse to hang out with the sand? Because it didn't want to sink to that level. So next time you mix something in water, take a moment to observe: is it floating, sinking, spreading evenly? You're not just watching, you're doing science. Take a moment to observe the world around us. You ever noticed how rice sinks but husk floats, or how oil floats on water while an iron rod sinks like a stone? Even a wooden stick stays on the surface while heavier metals dive straight down. So, what is the science behind this everyday magic? It's all about density. Definition for density is: density is the mass per unit volume of a substance. In simple words, it tells us how tightly packed the matter is inside something. Formula for density is equal to mass divided by volume. Here is the rule of thumb. If an object's density is less than water, it floats. If its density is more than water, it sinks. So, husk floats because it's light and airy. Rice sinks because it's denser. Oil floats because it's less dense than water. Iron rod sinks because it's way denser. Wood floats because its structure traps air, making it less dense. Think of water as a bouncer at a party. If you're light and relaxed, you get floating. If you're heavy and intense, you sink to the bottom. Why did the iron rod sink in water? Because it couldn't handle the pressure. So next time you drop something into the water, don't just watch, think density. You are witnessing a core principle of physics in action. Let's play a quick game. What do a crowded bus, a dense forest, and a sinking iron rod have in common? They're all connected by one powerful idea, density. Let's break it down. A crowded bus has lots of people packed in. That is high density. An empty bus, just a few passengers, low density. A dense forest has trees packed close together. A sparse forest, trees are far apart, less matter in the same space. Now apply that to science. Density is the amount of mass per unit volume. In simple words, how much stuff is packed into a space. So what decides if something floats or sinks in water? If an object is less dense than water, it floats. If it is more dense than water, it sinks. That's why husk floats but rice sinks. Oil floats but an iron rod sinks. A wooden stick floats but a metal bolt dives down. Think of water as a bouncer at a party. If you're light and relaxed, you float in, and if you're heavy and intense, you sink to the bottom. The same thing that we discussed earlier. So next time you drop something into water, just don't uh, watch. Think about the concept density. Let's settle a common science question. Does the shape or size of an object decide whether it floats or sinks? Well, here is the surprise. No, it's not about shape or size. It's all about density. Let's break it down. A small iron ball sinks. A large iron rod also sinks. Why? Because iron is denser than water. On the other hand, a tiny piece of wood floats. A big wooden log floats too because wood is less dense than water. So, whether it is big or small, round or flat, density decides the behavior, not the shape. Now, let's talk about gases. Does temperature affect gas solubility? Yes. And here is a twist. Higher temperature is equals to less gas dissolves. Lower temperature is equal to more gas dissolves. That's why cold water holds more oxygen, which is vital for fish and aquatic life. In warm water, oxygen escapes more easily, making it harder for underwater creatures to breathe. Gases are super sensitive to pressure. That's why balloons expand in heat and shrink in cold. The gas molecules inside are reacting to temperature and pressure changes. Hot water hugs more solute for solids. Cold water holds more gas for gases. And a little recap quiz. Why does oil float on water? Because oil is less dense than water. Which has higher density, wood or iron? Iron does. That's why it sinks. Can a small object still sink? Absolutely. If it is made of a dense material like wet. Why did the balloon feel nervous in the sun? Because it knew things were about to get intense. So, next time you see something float or sink or a balloon change shape, remember it's not magic. It's density, temperature, and pressure working behind the scenes. Let's wrap up our journey into the world of density, the science of how tightly packed matter is inside a substance. Units of density are: density is measured as mass per unit volume. The most common units are grams per cubic centimeter for solids, grams per milliliter for liquids, kilograms per cubic meter for gases and larger volumes. And a small conversion tips. So 1 gram per centimeter cube is equals to 1000 kilogram per meter cube. Same way, 1 milliliter is equal to 1 centimeter cube for water and similar liquids. So Converting between units is easy when you remember these relationships. Now let's see water as a reference. At room temperature, the density of water is approximately 1 gram per centimeter cube or 1000 kilogram per meter cube. That's why we often use water as a benchmark to compare other substances. So what does this mean? If a substance has a density greater than 1 gram per centimeter cube, it will sink in water. If it is less than 1 gram per centimeter cube, it will float. That's why oil floats and iron sinks. What helps us understand the behavior of materials in a simple visual way. Why is water so good at judging density? Because it always knows who is too heavy to hang around. So next time you measure, mix, or observe something floating or sinking, remember density is the key and water is your guide. Let's take a solid example. Literally, we have got an aluminium block with a mass of 27 grams and a volume of 10 cubic centimeters. So how do we find its density? The formula is density is equals to mass divided by volume. Density is equals to 27 gram. So if we divide 27 gram by the volume, which is 10 centimeter cube, that will give you 2.7 gram per centimeter cube. That means every cubic centimeter of aluminium weighs 2.7 grams. Pretty dense, right? Now let's compare it to water. Water has a density of 1 gram per centimeter cube at room temperature. So, aluminium is 2.7 times denser than water. This brings us to a new concept, relative density. Relative density is equals to density of substance divided by density of water. For aluminium, relative density is equal to 2.7 divided by 1, which will give you 2.7. So, a very important tip for this is relative density has no units, it's just a ratio. It tells us how heavy a substance is compared to water. So, what does this mean? Since aluminum is denser than water, it will sink, just like an iron rod or a stone. Why did the aluminium block sink in water? Because it did not want to float around the facts. So next time you measure mass and volume, remember density tells you how tightly packed a substance is, and relative density helps you compare it to water, our universal reference. Solve a kitchen mystery using science. You have probably seen oil floating on water, but have you ever wondered why? Let's think like a scientist. You pick up a 1 liter packet of oil and it weighs only 910 grams. But wait, 1 liter of water weighs 1000 grams. Hmm, something is different here. Oil must be less dense than water because even though both are 1 liter in volume, oil weighs less. Let's do the math. Density is equals to mass divided by volume. Density of oil is equals to 910 gram divided by 1000 ml, which will give you 0.91 gram per milliliter. That is lower than water's density of 1 gram per milliliter. So our conclusion is, since oil is less dense, it floats on water. It's not magic, it's density in action. This principle is used in cooking, chemistry, and even oil spill cleanups. Oil always rises to the top because it's lighter per unit volume. Why did the oil refuse to sink? Because it knew it was too light to go down. So next time you see oil floating on your dal or ghee rising in your pan, smile. You're witnessing density at work and you're thinking like a scientist. Young scientist, it's time to roll up your sleeves and get hands-on with activity 9.3. Today, we are learning how to measure mass using a digital weighing balance. Let's make every gram count. Step 1. First, switch on the digital weighing balance. Let it warm up and settle. Step 2. Check the display. If it is not showing 0, press the tar or reset button. This sets the balance to 0, so we start fresh. Step 3. Place a clean watch glass or butter paper on the pan. This keeps the pan clean and protects the object. Step 4. Note the reading, then press tar again to zero it. Now, the balance ignores the weight of the glass or paper. Smart, right? Step 5. Carefully place your solid object like a stone on the watch glass. Make sure it is centered and stable. Step 6. Read the displayed mass. Let's say it shows 16,400 grams. That is your object's mass. Always use clean tools and zero the balance before measuring. Precision matters in science. Even the tiniest error can change the result. Why did the stone feel proud on the weighing balance? Because it finally made a solid impression. So, there you have it. Measuring mass isn't just pressing buttons, it's about being careful, accurate, and thinking like a scientist. Right, kiddos, let's move from solids to liquids and learn how to measure them accurately using a digital weighing balance. Today's activity is all about precision, density, and a little bit of pouring magic. Step by step guide for doing this activity. Step 1. First, replace the watch glass with a clean beaker. This is where your liquid will go. Step 2. Place the empty beaker on the weighing pan and press tar. This resets the balance to 0, ignoring the beaker's weight. Now, pour your liquid like water or oil into the beaker. Watch the numbers change and note the mass displayed. Let's compare two liquids. 100 ml of water weighs about 100 grams. 100 ml of oil weighs only 91 grams. Why is the difference? Because oil is less dense than water. It has less mass per milliliter. This is why oil floats on water. Even though the volume is the same, oil is lighter. Density makes the difference. Some memory tip. Same volume is not equal to same mass. Less mass is equal to lower density, which is equal to fluids. Why did the oil feel proud in the beaker? Because it knew it was lighter but smarter. So next time you measure a liquid, remember you're not just pouring, you're practicing precision science, and every gram tells a story about what is inside. All right, students, let's settle one of the most common confusions in physics: mass versus weight. They sound similar, but they are totally different beasts. Ready? Let's break it down together. First, mass. Mass is simply the amount of matter in an object. Think of it as how much stuff is packed inside you, your pencil, or even your lunchbox. It is measured in grams or kilograms. And here is the cool part: your mass does not change. Whether you're chilling on Earth or bouncing around on the moon, you are still you. Now let's talk about weight. Weight is the force with which gravity pulls on that mass. So yes, it depends on where you are. On Earth, gravity is strong, so you feel heavier. On the moon, you would weigh less because gravity there is weaker. Weight is measured in newtons, named after Sir Isaac Newton, the guy who got bonked by an apple and gave us gravity. How do we measure that? Mass is measured using a balance. Weight, that's where spring scales come in. They stretch based on how much force is pulling down. Most weighing machines actually measure your weight, but they show it in kilograms. Sneaky, right? So when you say I weigh 50 kg, you're technically talking about your mass, not your weight. Mass is equals to matter. Weight is equals to W. V, because gravity pulls you down like a roller coaster. Let's keep going. Science is about seeing the invisible forces that shape our world. Have you ever wondered why we press that little button called tar before measuring something on a digital scale? It's not just for show, it's pure scientific genius in action. Imagine you're trying to measure the mass of sugar in a bowl. If you just plop the ball onto the scale, you will get the mass of the ball plus the sugar. That's not helpful, right? So, what do? We press start and boom, the scale resets to zero, ignoring the bowl completely. Now, when you add the sugar, you get the true mass of just the sugar. No cheating, no extra weight. We always want accurate data. Pressing tar helps us exclude the mass of the container and focus only on the object or liquid we are measuring. So tar, take away the container's weight. It's like telling the scale, hey, ignore the bowl. I only care about what is inside. The word tar comes from the Arabic word tar, T-A-R-H, meaning to subtract. So yes, even your scale speaks ancient math. Now go ahead and next time you use a scale, press the tar button like a true scientist on a mission for precision. How much space does it take up while measuring the volume of some liquid? Let's talk about something we use every day but rarely think about: volume. No, not the loudness of your music. I mean, how much space something takes up. So, what is volume? Volume is the amount of space occupied by an object or substance, whether it is the air in a balloon, the water in your bottle, or the milk in your morning chai. Everything takes up space, and that space is called volume. The SI unit of volume is the cubic meter, written as m to the power of 3. But let's be real. Most of us aren't measuring swimming pools every day, right? So, for smaller things, we use 1 dm to the power of 3, which is equals to 1 liter, perfect for measuring juice, water, or even petrol. 1 centimeter cube is equals to 1 milliliter or is equals to 1 cc, used in medicine, cooking, and science labs. The term cc stands for cubic centimeter and it is still used in medical prescriptions and engine sizes. So yes, your bike's engine and your cough syrup bottle speak the same language. Think of volume like packing a suitcase. The more space something takes up, the more volume it has. And just like you wouldn't measure your suitcase in meters, you use liters and milliliters for everyday stuff. Right? Children, let's get hands on with one of the coolest tools in the science lab, the measuring cylinder. If you have ever wondered how scientists measure liquids with precision, this is the hero of the story. What is it? It's a transparent cylindrical container marked with volume graduations. Basically, it's like a tall glass with numbers on the side, but way more accurate. Sizes? Oh yes, they come in all shapes and sizes. 5 milliliter, 10 milliliter, 25 milliliter, 50 milliliter, 100 milliliter, 250 milliliter, even 500 milliliter. So whether you're measuring a tiny drop or a whole beaker full, there is a cylinder for that. Now here is a trick. Always place the cylinder on a flat surface, no tilting, no holding it in your hand like a juice glass. And when you read the level, do it at eye height. Looking at the bottom of the meniscus, that little curve the liquid makes. Not the top, not the side, right at the tip. Meniscus is nothing but mini smile in the liquid. Read from the bottom of the smile, not the eyebrows. If you read from above or below the meniscus, your measurement could be off by a few milliliters. That's like adding extra salt to your recipe. Tiny mistake, big impact. All right, let's roll up our sleeves and dive into activity 9.4. We are going to observe and calculate like pros using a 100 ml measuring cylinder. Ready? Let's decode this tool together. First, what is the maximum volume this cylinder can hold? You guessed it, 100 ml. That is like a small juice box. Now, look closely at the markings. The big gaps between numbers, each one represents 10 ml. So from 10 to 20, 20 to 30 and so on. But here is a cool part. Between each big mark, there are 10 tiny divisions. That means each little line stands for 1 ml. Let's do the math together. ml divided by 10 divisions is equal to 1 ml per division. So yes, this cylinder can measure as little as 1 milliliter accurately. That is precision. Big marks is equals to big gulps, that is 10 ml. Small marks is equals to sips, that is 1 ml. This level of detail is why scientists love measuring cylinders. They are like the rulers of the liquid world. Alright, children, let's play a little lab deductive game. You have got to measure 70 ml of liquid, but which measuring cylinder should you choose? Let's compare your options using two key ideas, accuracy and convenience. Here is the lineup. 10 milliliter cylinder is super accurate, can measure down to 0.1 milliliter, but it's only good for tiny volumes. Measuring 70 ml with this, you will be pouring all day. 100 milliliter cylinder is balanced and brilliant. It reads down to 1 ml and it's just right for measuring 70 milliliter in one go. No fuss, no spills. 250 milliliter cylinder is good for large volumes but less precise. Smallest reading is 2 milliliter. So if you need accuracy, this one is a bit too relaxed. 500 milliliter cylinder. Great for bulk liquids, but the smallest reading is 5 milliliters. That is like trying to measure a teaspoon with a bucket. So the conclusion will be to measure 70 ml, the 100 ml cylinder is your best friend. Accurate and convenient in one smooth step. Choosing the right cylinder isn't just about size, it's about how precise you need to be. Scientists always balance accuracy with practicality. That's what makes them awesome. Smallest reading is how tiny a change you can detect. Convenience is how quickly and easily you can measure. So, don't just grab the biggest cylinder. Think like a scientist and choose the one that fits your mission. Champs, time for a quick quiz. Let's see how sharp your observation skills are. No picking at your notes, just trust your brain and go for it. Question number one. What is the smallest volume a 100 ml measuring cylinder can measure accurately? Think back to activity 9.4. You will get that 1 milliliter because each big mark is 10 milliliters and there are 10 tiny divisions between them. So 10 divided by 10 which will give you 1 milliliter per division. So it's a precision power. Question number 2. Why is a 250 milliliter cylinder less accurate than a 100 ml one? What is the smallest reading on the 250 ml cylinder? It's 2 ml, which means it cannot detect tiny changes as well as the 100 ml cylinder that reads down to 1 milliliters. Bigger isn't always better in science. Question number 3. How many centimeter cube is 200 ml of buttermilk? Time for a quick conversion trick. 200 centimeter cube because 1 ml is equals to 1 centimeter cube. So 200 ml is equals to 1 times 200 will give you 200 centimeter cube. Easy peasy. If you ever forget the milliliter to centimeter cube conversion, just remember milliliters and cubic centimeters are volume twins. Same value, different names. It's time to get practical. In activity 9.5, we are going to measure exactly 50 milliliters of water. Not 49, not 51, but spot on accurate. Let's do this step by step. Step 1. Start with a clean, dry measuring cylinder. No leftover drops, no sticky stuff, just a fresh start. Step 2. Place it on a flat surface. No tilting, no holding it in your hand. We want stability like a scientist's calm focus. Step 3. Pour water slowly until it reaches the 50 ml mark. Don't rush. Precision loves patience. Step 4. Need to fine tune. Use a dropper to add or remove tiny amounts. It's like editing a masterpiece. Every drop counts. Step 5. Now observe the meniscus, the curved surface of water. For water or colorless liquids, always read the volume at the bottom of the meniscus. Meniscus is already, as I told you, it is a mini smile. Read from the bottom of the smile, not the top, not the side. Step 6. Make sure your eyes are level with the meniscus. Looking from above or below causes parallax error, a fancy word for oops, wrong reading. Final step. Once you have nailed the 50 ml, transfer the water to the container unit. Mission accomplished. Even astronauts use similar techniques to measure liquids in space, just with a few anti-gravity tweaks. So, science is all about the details, flat surface, slow pour, bottom of the curve, and steady eyes. You have got this. All right, learners, let's zoom in on something that is tiny but super important in science, the meniscus. What is a meniscus? It's the curved surface formed by a liquid in a container. Ever noticed how water doesn't sit flat in a measuring cylinder? It dips a little in the middle. That is the meniscus. For water and colorless liquids, always read the volume at the bottom of the meniscus. For colored liquids, read from the top of the curve. Why is the difference? It's all about visibility, where the curve is clearest. Now let's talk about the design of the measuring cylinder. Ever wondered why it is tall and narrow? It's not just for style, it's for accuracy and precision. The narrow shape helps detect even tiny changes in volume. The tall design allows more graduation marks in a small space like a ruler for liquids. Less surface area means less evaporation and fewer chances of parallax error. And the shape makes it easier to align your eyes with the meniscus. No guessing, just clear reading. The taller and finer the scale, the more precise your measurement. It's like using a magnifying glass for volume. So, remember, the meniscus is your guide and the cylinder is your precision partner. Read smart, measure sharp. All right, let's clear up a classic lab mystery. How do we measure colored liquids accurately? It's all about understanding the meniscus, that curved surface formed by liquids in a container. For colorless liquids like water, the meniscus is easy to spot. It curves downward due to surface tension like a little smile. And here is the golden rule. Read the volume at the bottom of the meniscus. But with colored liquids like ink, syrup, or potassium permanganate, the meniscus is harder to see. The color masks the curve, so we flip the rule. Read the volume at the top of the meniscus, the highest point where the liquid touches the markings. So water, bottom of the curve, mini smile. Colored liquids, top of the curve, color cap. This difference in reading technique helps avoid errors and ensures your measurements are spot on, whether you're mixing chemicals or measuring cough syrup. So remember, water smiles from below, color stands tall at the top, measure smart, measure sharp. All right. It's time to bring out your rulers and think like volume detectives. Today, we are measuring the volume of regular shaped solids, specifically cuboids. That means anything boxy, notebooks, shoe boxes, dice, even your lunch box if it is rectangular. Step 1, pick your object. Let's say we are using a notebook. Step 2, measure its length, width, and height using a ruler or scale. For example, length is equal to 25 centimeter, width is equal to 18 centimeter, and height is equals to 2 centimeter. Step 3. Now plug those into the formula. Volume is equals to length into width into height. So, for our notebook, volume is equals to 25 into 18 into 2 will give you 900 centimeter cube. Volume of a cuboid is equals to length into width into height. Think of it like stacking layers of area to build space. Volume tells us how much space an object takes up, not just on the surface, but inside too. So yes, your notebook is secretly a 900 centimeter cube champion. So if you see a boxy object, don't just look at it, measure it, multiply it, and reveal its hidden volume. Today, we are diving into one of the coolest science tricks ever, measuring the volume of irregular shaped solids. Think stones, keys, marbles, anything doesn't fit a neat formula. And guess what? We are using a method that is over 2000 years old. It is called the water displacement method, based on Archimedes' principle. Yep, the same Archimedes who shouted Eureka in his bathtub. Here is how it works. Fill a measuring cylinder with water, say up to 50 ml. Tie your object with a thread and gently lower it in. No splashing, no cannonballs. Watch the water level rise. Let's say it goes up to 55 ml. Now subtract. Final volume minus initial volume is equal to volume of the object. So 55 minus 50 will give you 5 ml, which is the same as 5 centimeter cube. Displaced water is equals to hidden volume revealed. It is like the object whispers, this is how much space I take up. This method works even for oddly shaped objects like pebbles, rings, or tiny dinosaur toys. If it sinks, it can be measured. So next time you find a mysterious object and wonder how much space it occupies, don't guess. Use Archimedes' ancient wisdom and measure like a scientist. Let's unlock one of the most important ideas in science, density. It is the secret behind why some things float, others sink, and why a tiny metal ball can feel heavier than a sponge twice its size. So, what is density? Density tells us how tightly packed the matter is inside an object. It's like asking how much stuff is crammed into the space. The formula is super simple. Density is equal to mass divided by volume. Let's try an example together. If, say for an example, if the mass of an object is equal to 16.400 grams, volume is equal to 5 centimeter cube. Then plug it in. Density is equal to 16.400 divided by 5, which will give you 3.28 gram per centimeter cube. Think of density as a crowdedness of matter. More mass in less space is nothing but higher density. Water has a density of 1 gram per centimeter cube. So if your object's density is more than 1, it sinks. If it is less than 1, it floats. That's why oil floats on water and iron sinks like a rock. So if you're holding something and wondering why it feels heavy or light, remember it's not just about size, it's about density, the science of how tightly packed particles are. Children, grab your science helmets. We are heading deep into the earth. Today's mission is understanding how density changes as we move through Earth's layers. Earth isn't just one big rock, it's made of layers, the crust, where we live, work, and build cities. The mantle, hot, semi solid rock that flows slowly, and the outer core, liquid metal, mostly iron and nickel, and the inner core, a solid super dense ball of metal at the center. Here is a key concept. As we go deeper, density increases. Why? Because pressure and temperature rise the further down we go. The particles get squeezed tighter and tighter, like packing clothes into a suitcase for a long trip. Crust is equal to light, and rocky core is heavy and metallic. Deeper is denser. The inner core is so dense, it's like squeezing the mass of a mountain into the size of a city. That's why seismic waves behave differently as they travel through each layer. It is all about density. Remember, there is a whole world of layers below, each one denser than the last. Earth isn't just a solid, it is structured, scientific, and spectacular. Let's take a break from the lab and head outdoors because today we are learning science from nature. Ever seen a bamboo raft floating gently on water? It's not magic, it's density in action. So why does bamboo float? Bamboo is light, hollow, and less dense than water. That means the particles inside bamboo are spread out. It's like a feather in a shoebox. So, when you place it in water, it doesn't sink, it floats. Ancient people knew this trick long before textbooks. They used bamboo to build rafts and boats, trusting nature's design to keep them afloat. Smart, right? If density is like weight per space, bamboo is like a whisper in water. It takes up space but does not weigh it down. This is the same principle behind life jackets, pool noodles, and even ships. If the average density of an object is less than water, it floats. If it is more, it sinks. So remember, it's not just a plant, it's a natural engineer showing us how science and tradition go hand in hand. Let's dive into a concept that explains everything from floating balloons to ocean currents, how temperature affects density. When we heat a substance, its particles start to spread out. That means the volume increases and the density decreases. When we cool it down, the particles come closer, the volume shrinks, and the density increases. Hot, spread out, lighter, cold, packed tight, heavier. Ever seen a hot air balloon rise into the sky? It's not magic, it's science. The air inside the balloon is heated, so it becomes less dense than the cooler air outside. And just like a cork in water, the balloon floats upward. The balloon lifts off not because it's magical, but because the air inside is lighter than the air outside. This principle also explains why warm air rises in your room, why ocean currents move, and even how weather patterns form. So, remember one thing, temperature changes density, and density decides who sings and who soars. We have talked about temperature and density. Now, let's add another player to the mix, pressure. How does pressure affect density in different states of matter? Let's break it down. In gases, particles are far apart like dancers on a huge stage. When we apply pressure, they get squeezed closer together. Volume decreases and density increases. That's why compressed air feels heavier. It is packed with particles. In liquids, particles are already close together, so pressure has only a small effect. Liquids are nearly incompressible, like trying to squeeze water in your hand. Density changes just a little. In solids, particles are tightly packed like bricks in a wall. Applying pressure doesn't do much. Density stays almost constant. So, simple memory trick is that gas, big change. Liquid, small change. Solid, no change. This is why divers feel more pressure the deeper they go. Water's density doesn't change much, but the pressure builds up fast. So, whether it is floating ice, rising balloons, or deep sea submarines, remember pressure and temperature are the invisible forces that shape density. And density decides who floats, who sinks, and how things behave. Here is a chill mystery with a warm hearted answer. Why does ice float on water? Let's melt this question down with science. First, did you know that water is densest at 4 degrees Celsius? That is when its particles are packed just right, not too loose, not too tight. But when water cools to 0 degrees Celsius, it begins to freeze. And here is where the magic happens. The particles arrange themselves into a crystalline structure like a beautiful repeating pattern. This structure expands, increasing the volume while the mass stays the same. More volume, same mass, lower density. And that is the secret. Ice is less dense than liquid water, so it floats. Simple memory trick. Ice expanded, structure lighter than water. Floating ice isn't just cool, it's life saving. It acts like a thermal blanket, keeping the water below warm enough for fish and aquatic life to survive during freezing winters. So it's not just frozen water, it's nature's clever design, balancing density, temperature, and life beneath the surface. All right, curious minds, let's dive into a classic kitchen science experiment that is simple, surprising, and seriously cool. The floating egg challenge. Step 1, fill a glass with tap water. Drop in a raw egg. What happens? It sinks because the egg is denser than water. Step 2, now start adding salt and stir. Keep going, and guess what? Eventually the egg floats. Why? Because salt increases the density of water. When the water becomes denser than the egg rises like magic. This is the same reason people float more easily in the Dead Sea. It is packed with salt. Sugar water works similarly, but you will need more sugar. Syrup, already dense, so the egg might float right away. Glycerin or honey, thick and heavy, great for density experiments. To see this in action and explore variations, check out these awesome demos. Floating egg experiment shows the full setup and explains the science behind it. Eggs floating in salt water, perfect for demonstrations. And next time you are in the kitchen, grab an egg, some salt, and think like a scientist. Alright, children, from measuring tiny droplets in a cylinder to watching eggs float in salty water, this chapter has shown us that volume and density aren't just numbers. They are the language of matter. Whether it is the way ice floats to protect aquatic life or how hot air balloons rise into the sky, we have seen how simple measurements lead to powerful discoveries. We learned how to measure liquids with precision using the meniscus, how solids, regular and irregular, reveal their volume through shape or displacement, how density connects mass and volume and explains why things float, sink, or over, how temperature and pressure quietly shape the behavior of matter all around us. Every time you pour water, weigh an object, or watch steam rise, you are witnessing science in action. The tools may be simple, but the thinking is powerful. From bamboo rafts to floating icebergs, density helps us understand nature's design. And with every experiment, you're not just learning facts, you're learning how to observe, question, and explore. So, next time you see a balloon rise, a pebble sink, or syrup swirl, pause and smile. You now know the science behind it, and that is the real magic. Thank you so much for listening to my audio and watching my videos. Please do subscribe, like, and share. Once again, thank you to all the loving children.